Hi, my name is Suhani and this is my physics lab 2. The purpose of this lab is to visualize projectile motion in real life compared to computational models and compare the two models in order to explore the principles of Newton's second law and air resistance. In this experiment, constant velocity was in the x direction and velocity was affected by the acceleration of gravity in the y direction as well as drag. The first model was a paper rolled into a ball, which was thrown into projectiles that was tracked through an online program. The second model is two separate glow script codes that were modified to simulate the projectile motion of the ball with and without air resistance. In short, the findings of the lab were that calculating air resistance for projectiles is crucial to understanding the scope of net force of an object. The simulation with drag included was more precise compared to the drag tracker data, and the simulation without drag did not match up to the tracker data that well. This was used by comparing the x position and y position of all three models. And in this lab, the motion of the projectiles and their paths was also modeled. Some main physics principles and ideas was Newton's second law, which says that that force equals mass times acceleration, and this was used to calculate the gravitational force. The net force of drag is multiplying a proportionality constant, which is b, times the magnitude of velocity. And when adding these two, these create the net force, which shows the y direction and velocity of the projectile. In addition, these net forces were put into the position and velocity update formulas in coding as well as in calculations to calculate for b and as well to get the computational model correct. So this is a video of the tracker data and the points collected. There are 23 frames, 0.033 seconds in between, in which a spherical object was thrown across the table with a ruler behind for data collections. The system was a projectile while the surroundings were a table and the air as well. In addition, the initial conditions that were taken from this data and put into the computational model was 0.565 meters in the x direction and 0.625 meters in the y direction, as well as 1.38 meters per second velocity in the x direction and 0 in the y direction, because this was extracted from the very top of the projectile, because that is where the computational model begins. The time begins at 0.418 seconds with a delta t of 0.033. The magnitude of acceleration due to gravity is 9.8 meters per second squared, and the proportionality constant, which is b, is 0.0066. So this was the code that was used in the computational model. There's three main parts: the visualization, which shows a image of the actual projectile motion, as well as the initial conditions from before, b equals 0 for the model without drag, and b equals 0.0066 for the model with drag. And there's also a calculation loop which brings about the actual graphing and the data points. So this is the visualization and for the no drag simulation. And the 5 graphs that were created were x position versus time, x velocity versus time, y position versus time, and y velocity versus time, as well as x position versus y position. And this is the simulation data. And you can see a clear difference between the no drag and drag simulations. And this is all the data compiled together in the x and y direction. As you can see, the model with drag, the computational model with drag, is most similar to the tracker data. And this is a similarity, which indicates that it is crucial to add air resistance when calculating for net force of projectiles in order to mimic real life. And a difference was the tracker data and the simulation without drag, as the simulation without drag dipped significantly more than the tracker data, indicating that only calculating just Newton's second law, which is force equals mass times acceleration, is not enough for projectiles. Some errors in this experiment were calculating the proportionality constant, plotting the points in the tracker software, as well as human interaction when throwing the ball. All the projectiles were parabolas, and the equations used were net force of drag, force of gravity, position and update velocity, position and velocity update equations. And the conclusion is that drag makes projectile equations more accurate to real life. So for the two questions, the what does it mean question, the model with drag predicts terminal velocity as it becomes a horizontal line slowly, which the model without drag does not do. Therefore, terminal velocity is apparent when there is drag and air resistance. For the what if question, the time it takes to reach the ground is the same for both models because the velocity update formula only includes time in the y direction. So gravity dictates the time taken to land, which is the same.